Okay, hi everyone. I'm just going to show you how to do the few questions from acid-base equilibrium. Okay, let's look at question number one. Which of the following aqueous solution do not considerably change in pH when relatively small volumes of strong acid or strong alkali added? So what I'm asking is, which of the following aqueous solutions are buffers? All right, are buffers. So we know buffers are made out of a weak acid as well as its conjugate base, or it could be a weak base as well as its conjugate acid. So these will constitute of buffers, right? So over here, option number one, this is a weak acid, and F minus, right? F minus is its conjugate base, right? So which means this is a buffer. The second one, HCN is a weak acid, and Cn minus is its conjugate base. That's why it's also a buffer. And the third one, in fact, COH, right, this part here, this is a weak acid. Carboxylic acid is a weak acid. And over here, which is the COO minus, this is its conjugate base. All right, so which means this will also be a buffer. All right, okay, let's look at the next question. Right, let's look at the next question. Okay, which of the following could act as acidic buffers? So acidic buffers generally would constitute of a weak acid as well as its conjugate base. All right. So in general, for this question, you will notice that if I give you carboxylic acid as well as its carboxylate ion, which is the conjugate base, it will be a buffer. So let's look at these few options. So the first one is actually benzoic acid reacting with sodium hydroxide. So in fact, there's a reaction here. And you notice the ratio is 1:2, which means the carboxylic acid is actually in excess, right? So if I put in the numbers, this will be 2, this will be 1, this is 0. So when they react, right, since you're adding a strong base, you have to draw a full arrow. So this will be -1, completely react, -1 plus 1. So this will be 1, 0, 1. So look at the final line. F is final. So you see the final line, I would have some weak acid and some of its conjugate base. So that will be a buffer. In fact, it will be an acidic buffer. So let's look at next one. The second one, this is a strong acid, and this is a weak base, in fact, right? This is a weak base. You can take it as a weak base. So if you look at the ratio again, 1:2, so the weak base is in excess. So let's put in the numbers. So HCl will be 1, HCO3 minus will be 2, this will be 0. So when they react, -1, -1 plus 1, 1, 0, 1. So over here you can see at the end of the day you have carbonic acid as well as its conjugate base, which means it will also be a buffer. In fact, it will be acidic buffer. Okay, let's look at the last one. Again, HCl, which is a strong acid, and this is RCOO minus, which actually is a weak base. Sorry, right? So if you put in numbers and you see the weak base again is in excess. So if I put everything in, I have 1 mole of HCl, 2 moles of CH3CO minus, and this is 0. So -1, -1 plus 1, this will be 1, 0, 1, right? So you notice what you have at the end. You have some weak acid and you have some conjugate base that will also make it an acidic buffer. So in fact, the answer is 1, 2, 3. Okay, let's move on to the next question. Okay, let's look at this question. 0.1 mole per dm cube of aqueous sodium hydroxide is added to 25 cm cube 0.1 mole per dm cube of ammonium nitrate to form a buffer. What volume of sodium hydroxide must be added such that the final pH is 9.5? So having a final pH 9.5, this tells me it's going to be a basic buffer, right? Because the pH is more than 7. So this is what's going to happen. If you add sodium hydroxide, it will react with the ammonium. Okay, ammonium here, actually, you must know ammonium is actually a weak acid, right? So when sodium hydroxide, we have ammonium, all right? So there will be a reaction. It's a strong base. Take this as a strong base and a weak acid kind of reaction, weak acid. So when they react, you form ammonia and water, okay? So let's try to find out the number of moles of ammonium. So number of moles of ammonium is calculated from 25 over 1000, which is the volume, multiplied by the concentration. So this will give you a value of 2.5 times 10 to the power minus 3 moles. So let's see how we're going to do it. Let X moles be the amount of sodium hydroxide. So this will be X. And ammonium will be 2.5 times 10 to the power minus 3. So when they react, since it's going to form a buffer, this ammonium must be in excess. So all the sodium hydroxide will have reacted, minus X, and this is plus X. So eventually, the number of moles of ammonium will be 2.5 times 10 to the power minus 3 minus X, and here's X. So at the end of the day, you have ammonia, and you have ammonium, all right, which makes it an alkaline buffer, all right, So how are you going to complete this? So since it's alkaline buffer, I'm going to use this formula. POH is equals to pKb plus log, the salt in this case will be ammonium, over the base. So let's put in the numbers. Since the pH is 9.5, we can calculate POH, which is 14 minus 9.5. That will give you a POH of 4.5. pK is calculated minus log Kb, and we actually have the Kb value, which is 1.6 times 10 to the power minus 5 plus log. So the concentration of ammonium is actually 2.5 times 10 to the power minus 3 minus X. Okay, I just put divide by the volume to get the concentration. The ammonia will be X over the volume. But notice the volume will just cancel out. Okay, so you have an equation with only one unknown. Try to solve it, and X will turn out to be 0.00166. All right, moles. So what's the question asking? The question is asking for the volume of sodium hydroxide. So in order to find the volume of sodium hydroxide, we know that concentration equals to moles over volume, which means volume is equals to moles over concentration. The moles will be 0.00166. Okay, the volume, the concentration is 0.1. That will give you a value of 0.0166 dm³, which is equivalent to 16.6 cm³, right? So this is how we do this question.